welcome back to our course. Let's recap what we learned yesterday and then cover some new material today. We started off yesterday with the set of equations here, not this set of equations, with the set of equations there, right? So this is the equilibrium set of equations for the New Keynesian climate model that we discussed now a lot of times. And then we spent time yesterday on the computer familiarizing ourselves with how can you code this up into linear. There are two things that are important here. The first one is it's a nonlinear model, so we learn how to specify a model in linear with nonlinear equations. Familiarizing ourselves with how then we are solving this model, right? Which involves two steps: the steady state and NMs. It turned out that the steady state can be complicated, and we need actually a numerical routine to solve for the steady state. That was the F solve. We learned that sometimes nonlinear models are so complicated that you cannot solve with pencil and paper for the steady state. So after we learned that, we then familiarized ourselves with a solver, with a new solver, to solve this nonlinear model, which is the so-called perfect foresight solution or solver. And it has different names: the time stacking, the perfect foresight solver, the two-point boundary value. And we learned that in linear there is a very straightforward command to invoke that solver, and then we were playing with this and learned how to actually work with this model quantitatively. We then also looked at the replication codes and started to run those replication codes as well. So long story short, you have not only the set of equations, but now you understand also how is this solved, like what's the big trick, and how does that compare to previous results. And so that was an important part of our lecture yesterday. And then we launched into the estimation, and the idea was for you to understand this intuitively. So the authors are estimating the model using 4 time series, the GDP, inflation, the interest rate, and emissions for at the world level for the sample from 85 to 2023. And then we familiarized ourselves with some of the intuition underlying the estimation procedure. That is, the dots are the sample, right? The dots are the, let me just do that. The dots are the sample, so those are observations. And then the model has trends, so that's the solid blue line. And then we're looking for shocks that explain the model, that explain the data step by step. So observation by observation, the filtering is done to search for these shocks. And of course, importantly, the model has a set of parameters, so there's a vector of parameters, and the authors are estimating it by going through this iteratively. So they're going through 1 to 4, or iteratively. So they are starting with some parameter values. Then they're going to compute the path, the blue line, and they're going to find the shocks that match the data, the green line, and then they're going to compute the likelihood function. And then once they have that, they are iterating over this by choosing a different set of parameters, and they're doing this to find what parameter values maximize the likelihood function. That's what it does. And then once everything is said and done, they then go into the last observation that they have, and then they do long-term forecasts. Okay? That is, so to say, the next step in the analysis. And the one thing that we discussed as well was that they have this carbon tax they're putting in, and they're considering 3 cases. They consider the case when var phi is equal to 1, meaning that the carbon tax increment in the model is the same as the carbon tax that is, according to the model, needed to bring emissions down to 0 by 2050. So that's the Paris Agreement. And when the Paris Agreement, so to say, is taken as credible in the model, there is a path, pi star, that looks like this. We're going to put in that pi star, and then emissions by 2050 will be 0. And then there's 2 alternatives. One is when phi is equal to 0, and that means the agents are planning with no carbon tax. And then they allow this parameter to be estimated as well. So those are the 3 cases that the authors always consider. We discussed the set of estimated parameters, and most of these parameters you'll see in the computer codes. And then we looked at what the shocks, the paths for the trends looks like, right? And we launched then into the analysis part, right? So now we're looking into these long-term forecasts. And again, the authors are going through these three agreements, or three cases all the time in their analysis. Right? So they always compare the Paris Agreement, which is the Pi-star path. Then they go for what they call a laissez-faire, the business as usual, with phi equal to 0, and then the intermediate case with the estimated version of the model parameter. So that's what they always have. And then we're getting these types of graphs, and where they actually show the model forecast. Okay? So this is starting in 2023. This is the model forecast in 2023. In case you're wondering why we have these kind of big run-ups here in inflation, right? Because that's of course because inflation did increase sizably at the end of the sample, right? So this is the rate of inflation, and this is inflation at the end of the sample. So this is the last observation that they have in the sample. And then they are forecasting from there. And so if you ever wondered why are these, in the plots here, why are they, so large initially? That's because of the initial conditions coming from the data. And then of course the shocks are fading away, and eventually only the climate element is going to be, left over. Now that's something that we didn't do yesterday, but you can produce these plots yourself. And so that's something I think we did not cover together yesterday. So let me show you where you can produce these plots yourself using the replication codes. That's something that we unfortunately did not cover. So let me just find that real quick and show that to you. Okay, so we looked at, these are the files from the replication code kit that, is on Moodle, right? And yesterday we ran, we looked at this replication code kit, we looked at this model file which implements all the equations, right? And then the one thing that we ran yesterday was run IRS.mod, right? And then it took like a couple of minutes to do all these computations, and we got these impulse responses to the shocks, right? The one file that we didn't run together yesterday, for time reasons, was run simulations.mod. So if you run that mod file on your computers, you're going to get the plots that we're discussing next. You're going to get these scenario forecasts, the simulation going forward plots with the three cases. Paris Agreement, laissez-faire, or the intermediate value. So those graphs are produced in this mod file. Very straightforward to run, and then you can of course play with it, right? You can assign different parameter values and change, so understand how do these trajectories change. All right, so then what we did yesterday as well is we again went through this analysis, and we started with a laissez-faire, so when there is no carbon tax whatsoever implemented. And then we familiarized ourselves with the idea that, well, in that case, when there is no carbon tax implemented, emissions are going to be what they are. They are like evolving. They're actually going to go up, right? And then that produces a decline in productivity. So that explains why output is going to fall and is going to keep falling throughout the simulation horizon, right? Because of this increase in emissions being detrimental for productivity. As a result, because of worse productivity, we understand marginal costs increase, right? And that triggers a run-up in inflation, and that was what we discussed here with this red line. So this is the trajectory of inflation in this model. Now notice, right, this is 2023. By 2030 or so, all the shocks have faded out and faded away. So there may be some leftover shocks here from the last observation, right, from the last period in the sample, but within 10 years, all these shocks are going to go back to zero. So in intuitively, by this time, roughly toughly, there's no shocks in this model any longer. And it's only the model, how it basically develops, in terms of the recursive elements of, the emissions and so forth. And we then learned that, with the red line is the laissez-faire, that's what we call climate-inflation. It's because of the emissions being high, inflation is going to stay elevated relative to the target of the central bank. And quantitatively, this is in quarterly units, and we kind of went through, say, take this window between 2030 and 2060. You have to annualize some sort of the average, and that's about 2% above the central bank's target, which is huge. It looks small, but it's huge. Now, then we have the Paris Agreement, which is the carbon tax being chosen in this model so that emissions are going down to zero in an almost linear fashion by 2050. So that was the other important analysis here. And then we can see two effects. First of all, because of the carbon emissions, we see that output is going to fall faster or more in the short run compared to the laissez-faire. So it's more costly in the short run to implement climate policies. And the reason is that there's twofold. First reason is that there is abatement investment or abatement spending, which crowds out private consumption. And second, because of the carbon tax increasing marginal costs, inflation goes up by more, and thereby the central bank raises the interest rate more. We'll discuss this today in more detail. So you have two forces why in the short run this falls by more. First, because of the mitigation spending crowding out private consumption. Second, the central bank, to fight inflation, raises the normal interest rate by more. That's what you see here. Normal interest rate goes up by more than in the laissez-faire. And that more increase in the normal interest rate is going to slow down private, aggregate spending. So that's the short-term cost, but then there's a long-term gain in the sense that what you see is that starting in the 2040s or so, this model predicts that output is going to be higher or larger than in the laissez-faire. Okay? So that's basically then reflective of that. This negative feedback loop from emissions onto productivity is broken. That's not there any longer when emissions are zero, or not. It's not there, but it's smaller in size, and that's why actual output can exceed then the laissez-faire. And then the estimated case, the blue, is somewhere between those two equivalent cases. Okay, so that's what we learned yesterday. Are there any questions? On inflation?
Yeah. So originally we say that the reservoir, the red one is the climate inflation, and the second one is the combination of that. But we cannot integrate too easily as like plus, because there may be like interaction between those.
That's right, because
many more things.
You're right, Louis, right? So we discussed exactly. We said that the green line now embeds both climate inflation and greenflation, right? That's the sum of the two. But because the model is non-linear, these things don't add up. So the delta between the red and the green is not just greenflation, because it's a non-linear model. If the model were linear, we could just add them up, right? If the model would be entirely linear, then you could basically just stack and you say the delta is emissions. But, long story short, for you, intuitively, it's okay to think about as this gap representing, for the most part, the emissions, the green inflation part. I mean, quote unquote, right? I mean, that's one way to basically think about it. I think it's a good approximation, although it's not going to be precise, but it's intuitively a good way to think about that additional delta is coming from greenflation. Other questions? All right, we've come pretty far. Go ahead. Can you say that again? Sorry.
We also have
Yeah.
climate inflation in the green line because
Yeah.
Because it's of the existing carbon.
Totally, right? Because look, there is climate-flation because there is still emissions in the transition, and the level, of course, of the stock of carbon is still elevated, right? So even with the with the carbon tax, there is still, you know, a detrimental effect on productivity. So that's why, I mean, this was maybe the annotation was like when we wrote it yesterday, right? So this is climate-flation plus greenflation. So this green line, right, embeds both forces now, right? It embeds the climate-flation force and it embeds the greenflation force. But you're absolutely right. That's what I was saying. Be a little cautious, but because here in this green line, the climate-flation force ought to be smaller than in this red line, right? That's the key idea. Because we have less climate damage in this green line. You know, that's why, you know, if you were to decompose this, and we're going to see this in a little bit, you're going to see that the climate-flation element is going to be smaller here than there because there's less damage than here. So, we get back to that idea, okay? Because what this all points to, oh, are there other questions, sorry? Are there other questions? So we are going to come back to this now because, you know, Min asked me something yesterday, Hui, Ivy, right? Your questions are reminiscent of the desire to understand where are these results coming from and how can we decompose these results, okay? To develop more intuition of what's coming. Okay? And so that's why the authors offer a decomposition of the IS curve, and we're going to discuss this next. And after that, we're going to do a decomposition of the Phillips curve. So we're going to, you know, slice the model apart. And actually, I'm going to come back. You know, here we will be in this Phillips curve part. We will be able to decompose this into climate-flation and greenflation. And I'm going to talk a little more. One of the caveats of this decomposition because it relies on a linear decomposition of the non-linear. Otherwise, it's very hard to do. So. Right, we'll talk about that. So let's get started then with what the authors call dissecting the IS curve, right? So this is a decomposition. This is a decomposition. It's a decomposition of inflation, or no, sorry, of output. So Y is output, that's GDP. Okay? So that is GDP. And it's decomposed into consumption, C, plus green investments, I'm going to call that IG for green investment, plus all the normal adjustment costs. Okay? So there's also spending if you change your prices or the firms who go bankrupt or go exit the market, their profits just disappear. So this is like the nominal wedge, what they call it. Okay? So what we can decompose now, the GDP response we observe, into consumption, investment, and the nominal wage. That's the plan. And so that's what we have here. So again, you can think about this as being GDP here, and then this is consumption, and this is IG, and then this is just the nominal wage. So this is the overall results. Now this is work in progress. If you really have sharp eyes, this is not exactly the same as this. So if you have really sharp eyes, right, so this is not exactly the same as this. So you have to take this with a grain of salt. Most likely what happened is that they haven't updated the decomposition with the latest results. So this is, so to say, coming from the paper with the latest results, the latest estimation results, the latest stage of the paper, and this must be a version of the paper from an earlier instance, and so this is not exactly the same results up there. That's something for you to keep in mind. This is work in progress. This paper is not yet, will be published in a fantastic journal, but it is not yet published, and so those would be. We have to monitor that a little bit. Regardless, it is useful to now understand that it has the same features, right? With the Paris Agreement, output falls more in the short run than with the laissez-faire, and and then in the long run, it's exactly the opposite. That output doesn't go down as much as with the laissez-faire in the longer run. So this is all consistent qualitative. Okay, so now let's take a look at what we see here. So GDP falls, and we can now, using this linear decomposition, right? Notice the heads here are linear, so this is log linearized. So it's a linear decomposition. So this is a linear decomposition. That's very important. We have a nonlinear model, but the way you can make progress on the decomposition is by linear, because then you can add up the total effects. Okay, and what you basically see is that like this minus 5% decline of GDP in the short run is driven to the most part by this minus 9% decline in consumption. So consumption really drops like a rock in this economy in the short run, while abatement expenditures actually surge. So that's the idea, that private consumption goes down a lot, and abatement expenditures goes up a lot. And then if you take this, plus this, then you're going to get the green line that we see here. So you see there's a horse race here in the sense that private consumption drops a lot, investment spending in the green case goes up a lot, and then the nominal wedge it is what it is. It's a function of inflation. So that's basically the idea that we have these two forces against each other. Now, one important force is that the monetary policy. The question is, why does this go down so much? What's the reason why does private consumption go down so much? It goes down like a rock. And here you would think maybe let's write down the very special, easy version of the consumption-Euler equation. So the Euler equation for consumption says something like this, right? You can write this as Ct plus 1 divided by Ct is equal to Rt over pi t plus 1. I'm leaving out expectations operators here. So this is having no expectations operators. And what happens is that when inflation goes up, because of the central bank's reaction function, the nominal interest rate goes up by more than 1 to 1. So what's happening here is that the central bank is responding to that by increasing the real rate. That's what the central bank tries to do. And that means consumption growth must go up. Now when consumption growth must go up, the level must first go down and then it must rise. That's the idea. And that's what we see here. Consumption growth is in the sense it first falls, but then it's going to start going up at some point. So long story short, the idea is that when the central bank raises the nominal interest rate quite a bit, it's going to dampen the consumption response. So the long story short is that if the real rate, goes up, consumption goes down. That's the idea. And that's triggering this rather strong fall in consumption that we have under Paris. Okay. But then going forward, right, because we're going to have less emissions, we're going to have the stock of carbon in the atmosphere is going to be lower. That means then going forward, we can sort of say, at some point consumption, is going to stabilize in relative terms, and then the abatement spending is going to kind of take over, and overall GDP is elevated relative to the laissez-faire case. Okay. Are there any questions on the Paris Agreement effects that we see here? So keep in mind, monetary policy is an important player in this kind of environment here, that it aggravates the recession. Right? The central bank trying to stabilize inflation, right? Inflation runs elevated for some time. The central bank tries to stabilize that. That's a further down force on consumption. That's the key. Then let's go to laissez-faire, right? Under laissez-faire, we have similar results, right? The central bank also counter forces the inflation surge by keeping a high real rate, right? So, but consumption doesn't drop by as much because we don't have that crowding out effect from the abatement spending. So the red line here, there is no abatement spending, so firms don't spend on abatement, so that doesn't crowd out private consumption. Always think about this. output can be used for, say, abatement spending and consumption spending, and if there is no abatement spending, there's more consumption possibilities left over for the households. But if firms spend like crazy on abatement, that eats away, that drives up the price for consumption, so households are going to consume less. That is this green line. So as a result, with laissez-faire, you see that the drop in consumption is much, much smaller. Okay. So here consumption only drops by 2%, while there it drops by 9%. So that difference here is because of monetary policy and abatement spending. And if you take abatement spending away, you're just going to be there. Monetary policy, even in this economy, still fights the inflation effects. So you can think about that, this drop in consumption is mostly the monetary policy response. That's the higher response in policy. But again, this is all non-linear, so you've got to be careful with interpreting this. This is a linear decomposition, but you've got to be careful with interpreting this, to the digits when you think about the non-linear. The one thing to notice is that, notice this one, right? Because the damages keep growing in the laissez-faire, at some point you're going to have this crossing, even though that's toward the end of the century. You're going to be grandchildren. You're going to have grandchildren at that point. the consumption is going to start to come lower in than under the green, under the Paris. But of course, this is far in the future, and okay. So any questions on this? So you can always try to decompose the results to understand where the bits and pieces come from. And let's try to do the same on inflation. So here we have the decomposition of the Phillips curve. Okay, so this is the decomposition of the Phillips curve. And so what you can do is, the way to think about this is that you can split the marginal cost term in essentially 3 elements. Okay? So the first element that you can split in the marginal cost term is the real wage term, right? So the real wage term is the first object, right? That's the one part of marginal cost. And then we have these 2 extra terms. One is the climateflation part, and then the other one is the greenflation part. So we have these 3 terms. And then when you take this into the Phillips curve, so if you take this here, we just take this to the equilibrium set of equations, right? And you plug that into the Phillips curve, and then you log linearize the equation. Good morning. Then you're going to get the following results, right? So you're going to get that decomposition of the Phillips curve. There we go. You get that decomposition of the Phillips curve. So 7 is the log linearized New Keynesian Phillips curve with the climate change. And you're going to have 4 drivers, essentially. Okay? So you can decompose inflation into the wage term, the climateflation, the greenflation, and then the exogenous shocks. Those are obvious, right? And what do they mean by exogenous shocks? Well, this is an exogenous shock, the emissions shock. And this one's also exogenous, like a shock. This is the decoupling. Okay? Even though it's deterministic, but you can think about this as a shock as well. And then also this abatement thing. So that's what they're all lumped into this way. But for the most part, try to think about this. And then you can calculate these objects and display them. So slide 46 has to be deleted, but slide 47 has the results we want. So this is total inflation. So let's write this down. So this is pi t. Okay. And then we have pi w, which is the wage component. Then we have pi climateflation, which was abbreviated with pi c. Okay. So this is pi c. Then we have the greenflation force on inflation, and then we have the exogenous force. Okay. So again, those are our results on inflation that we had observed or that we have studied as a total. And Min asked yesterday, where does this come from? And this now allows us to understand where are the forces operating here that drive inflation. And what you can see is that regardless of whether you are in the Paris Agreement, in the estimated path, or in the laissez-faire, wage inflation falls. Wage inflation actually is negative. So meaning, in this economy, because of climate change, the hourly wage is going to deteriorate. The hourly wage is going to fall. Okay? That's an important element. So if this model is right, we're all going to earn less money per hour in the next 75 years relative to the case when we disregard climate change effects. That's how we have to think about this. So I see wrinkles on Vince's forehead. So why is that? That's a fair question. Okay. And there's now several forces that can explain that. Why we have that. And you know, the fall in the wage. So one thing is what's called the general equilibrium effect on this, and the way to think about this is as follows. Who supplies labor to the labor market? It's the households. And households in this economy, right, they are really getting poorer because of climate change and climate policy. And the way to see this is that the consumption response really makes them poorer, right? So the consumption response is like, look at this, like you lose 10%, you lose almost 10% of your consumption. So you are permanently poorer. You're really almost permanently poorer because of climate change. And even absent any climate policies, even laissez-faire, you are poorer. What do people tend to do when they are poorer? With your labor supply, with your labor effort. So suppose you make 10% less income. How would you try to compensate for that somehow? How would you try to do that? You work harder, you work longer. You increase your labor supply. That's exactly one force that's at work here. So the way to think about this wage effect is, it's an effect on labor supply. So there is this labor supply effect, let's write this down. So this is a labor supply effect. So the way to think about this is, you know, let's just depict, we have a Varese labor market here, so let's just depict labor or hours worked on the x-axis and the wage on the y-axis. And then we have a labor supply equation, LS, and then we have a labor demand equation, LD. So that's a standard labor supply, labor demand frame. If you are permanently poorer, you're going to increase your labor supply, trying to make up by supplying more hours to the labor market. So how could you show this in this graph? How could you visualize this in this graph? The LS shifts down, right, Juan and Min, right? So the LS would actually shift down, right? So that's the LS prime. And then you see there is a new equilibrium, right? Where you're going to have a new equilibrium relative to the old equilibrium, that you're going to increase your labor supply, but it's going to come at the cost of a reduction in your wage. The old equilibrium was this point, the new equilibrium is this point, right? You're going from point A to point B. So you're starting in point A with a nice juicy wage and some 8-hour work days, but because you're poorer, you're extending your labor supply, you're going to go to more hours and having a lower wage. So that's the one force that drives down the wage. Okay, there's this labor supply effect. Then there, of course, is also a second effect, which is the productivity effect again. Because labor productivity falls because of climate change, right? Because of the carbon in the atmosphere, the droughts, the flooding, the heat waves, productivity of labor is going to be lower, so the wage is also going to be lower because of the productivity effect. So the second one is a productivity effect. Falling, and the way to think about this, the productivity effect falling is, think about this as YT, right? Again, output is equal to, you know, we have this negative function f phi m t of LT. And when you have climate change, this thing is going to go down. So every hour that's being worked generates fewer goods of output. And the factor of labor is compensated by less stolen wages on the farm. So that is the second effect. Because of that, the wage is also going to drop. So two forces that lead the wage to decline, the labor supply effect and the productivity effect. Now you can think about that. The red line here is only having this productivity effect because there is no abatement spending in the red line, right? So with the laissez-faire, there is no abatement spending, so you only have the productivity effect. But when you have added abatement spending, you're going to get the green line. Okay? So that difference you can interpret as, for instance, the labor supply effect. Because agents in the green line are so much poorer than in the red line, initially in the short run, they are extending their labor supply even more, so that is going to compress the real wage even further. All right, so that's the idea on the wage part. And then we can kind of get back to Ruiz's question and also Ivy's question on the climate versus greenflation. So this isolates now just the climate inflation effect. So the effect of inflation, of climate change on marginal cost. And you're going to see with the laissez-faire, you're going to get an ever-increasing effect on inflation. So the effect is going to get larger and larger and larger and larger. And so that effect is going to go through the roof. This effect is going to be dampening that. Okay? So that's why the total rate of inflation looks relatively stable, right? Because this plus this, is going to be equal to this. That's the key. So you have this force that climate inflation is going to go up and up and up. So if you measure that, but the wage component is going to go down, down, down because of the damages. Now, when you are doing, let's say, when you're going to go for Paris, right? You're going to go for the abatement and for the carbon tax. You're going to see there is a dramatic effect coming from the climate inflation part. And so climate inflation is much lower than in Paris than in laissez-faire. And that's exactly that what you asked is when we discussed these graphs, when we discussed the overall graphs, right? I said be careful. The green is climate plus greenflation, but the embedded greenflation here is going to be smaller than the greenflation that we have here, right? This was very sharp of you to think about it exactly this way. And the better way to see this is exactly with the decomposition that we do right now. You can really quantify now the effect. And you see that the climate inflation part is so much smaller with Paris than with the laissez-faire. But of course, the flip side is now, we're going to get. So this is great. So then, if you just plot these two together with these two. It's not really clear, right? This is down by more, this is up by more. This is down by more, this is down. So if you add -5 and what is it, maybe 1% or so, then you're going to be at -3, right? So inflation would be actually deflationary here. If you just add those two components. And if you take this and that, this is like -2, this is about +2-ish, so then inflation should be around 0. So something isn't adding up yet here, right? And that's, of course, for the Paris part, there's a lot of extra inflation coming from the carbon tax. So the carbon tax, because there is more spending on abatement, like firms are really buying a lot of abatement technology, filters and, solar panels and all the things that you can imagine. That is, of course, increasing demand, and that demand pressure is going to push up inflation for those elements. So that's the greenflation part. You see that the inflation part can be really sizable here. And in fact, it is very sizable. These shocks are these are the exogenous shocks. You see they're going to fade away. There's still, some there, but importantly, those exogenous shocks are identical in both model versions. So they don't differ by laissez-faire versus climate change policies. Yeah. So what's the basic bottom line here? Right? Be careful. Be careful in terms of what's driving the overall inflation responses, and be mindful of what are the forces at work in the model that generate the aggregate responses. And the model is very helpful in decomposing those forces. Alright. So then, this is I think in words everything I said already, right? Under laissez-faire, we have exactly the type of things I just described in words. I don't think we need to repeat those words. Any questions?
Can you explain a little bit again about the shock? Because I see the term the shock both involve the mu, which is like the given, and then the
Right.
epsilon e, which is the shock
Right, right, right.
condition. So they like
So right. So intuitively, think about this. But be more careful. We have in total 4 shocks. So it is all the 4 shocks in this model affect, of course, inflation. So let's go back to the model equation. Let's go back to the equilibrium equations of the model to locate once more where do we see the shocks in this model, right? So what are the equilibrium objects that we call shocks in this model? And there's 4 shocks in this model, right? So there is, first of all, there is this demand shock, EP. Then we have this Phillips curve cost push shock, EP, right? Then there is the monetary policy shock. Oh, they lost it here. There's because it's overlaid, it's superimposed. So behind this green square, there is the monetary policy shock. That's the 3rd shock. And then they have this emissions shock, epsilon E. So they have 4 shocks in this model. And then when they estimate the model, right, they are estimating the model on 4 time series. So let me go to the estimation part. There we go. Right, so they estimate this on 4 time series. So the reason why they have 4 shocks is they want to explain 4 time series. And in this model, the way this estimation technique is, you need to have as many shocks as you have time series. All right, so that's where we have 4 shocks. Now, then they explain the data with the model and the 4 shocks. But of course, if you think about this from an observation perspective, the last observation, that last dot there, right? You have 4 dots. You have a dot for inflation, you have a dot for output, you have a dot for emissions, and you have a dot for the interest rate. Okay? So then what you need to have is you have 4 realizations of shocks, right? You have the 4 structural shocks, and you need in that last quarter, to get that observation, you need a realization for the monetary policy shock and for the technology, for the cost push shock and the emissions shock. So those are 4 shocks, and all these 4 shocks, they affect inflation. Okay, so if you look at the impulse responses from the replication codes that we looked at yesterday, right? If you compute what is the impulse response to the demand shock, what is the impulse response to the tau shock, to the emissions shock, and so forth, you will see inflation is always moving. So that is all the 4 shocks move inflation. And that's what this pi x means. Okay? It's the contribution that all these shocks have on inflation. So that's something for you to keep in mind. Let's see, where is this? There, right? So the easiest way to see this is obviously this, but by a general equilibrium effects, there's of course other shocks, that's like the demand shock and so forth. They're all featured in here. That's clear. Okay. More questions? It's quite beautiful, honestly, isn't it? That you are able to rip this apart and so to say get so much richness and intuition for the driving forces of the model, like what affects what. And you can see this quantitatively and how different it is. I mean, these differences are huge if you think about it. Like this is like a 2.5 percentage point difference. And that's of course also huge. And how they are when you're netting this out or when you add them up, how they produce something that is on the far left over there. So always try, if you can, in your research or when you're reading papers, try to decompose things to make sense of the economic intuition. And so then, are there any questions on this? Now, some of you, when we have developed the model, may have had thoughts on, kind of interesting, but it's also quite stylized. I mean, we are describing the world with 4 equations. Right? We're aspiring to explain the world with 4 equations. Right? When we have, I mean, the data we're using, this is world data for output, world data for interest and inflation and emissions. And then we are saying, we're taking 4 equations and we explain how the world works with 4 equations. I mean, either you have these thoughts, or if you explain this to your grandmother at dinner, or your mother, or to your bosses at some point.
It's not to
Go ahead.
the intention.
Yeah, exactly. So, if anything, it's a tool for intuition, but there are these nagging thoughts that maybe isn't the model too simple and too stylized? And couldn't we get other results if we make this model more quote-unquote realistic? And how would the results look like then? That's the big nagging question. And that's why this is an amazing paper.
I think yesterday we had a kind of like similar kind of discussion.
Uh-huh.
Because my impression is like, you know, everything that we learn now is like we learn from hindsight, right? This is the result, and you kind of like explain it to us, right? And the thing is like, my question is like, if we play the role of someone who actually designed a model
Yeah.
from the beginning,
Yeah.
how can you come up with the kind of structure that is so like very mathematically very elegant?
Uh-huh.
Isn't like the whole thing, a lot of things like is governed by a few key parameters.
Yeah.
When you switch on and off, you create a kind of like counterfactual analysis between different scenarios.
That's right.
So from the beginning, if say like I want to try to describe too much about the world, right?
Uh-huh.
Maybe somewhere in the middle, my math become very messy and
That's
it
right.
doesn't have this kind of like tractability that is showing here. Right?
That's exactly.
And it's always like kind of a question about how they get from to there. Because now you're showing the result to us and from hindsight and you explaining back and then everything makes sense. Right? But how can they, you know, from the beginning, do they have some kind of like expectation that okay, this should be the kind of structure that I need to provide?
Yeah. Now, so I mean, there's different ways to answer your question or to react to your statement. And one is, you know, these guys have an incredible amount of experience. They're like, you know, Frank Smets, he did, you know, top-notch macro research for 30 years. He's now, you know, in his, you know, senior phase of his career. He's a very, you know, important person in not only the research but also policy making. And essentially, like, he did this for 30 plus years since his PhD working on these models. So he knows a lot about the details, what features of a model are required to explain certain features of the data. So there's returns to experience. And Gauthier, Fernandel, and Jean-Pierre Sahu, it's the same there. They also have lots of experience. They are more younger than Frank, but they have a great pool of experience. And then certainly the way this goes is they didn't only, I mean, so then they're trying to get this as Lin said, as intuitive as possible to develop intuition, to explain the mechanisms. But they certainly did not just write down those 4 equations from scratch and arrive those. They had more complicated versions of this model. And then they looked at more complicated versions, and there's a trade-off. You have more equations, and as you're saying, right, then you have a mess. It's not so beautiful, it's not so intuitive what's going on there. So there's a trade-off there. And you have to think about it a little bit like a paper is also a lot of marketing. How do you write a research paper that is accessible? That, for instance, I can use to teach you guys about climate change. If we had a model with 15 or 20 equations, it would be much more complicated to use. So I think there's no perfect answer to your question or to your statement. You know, that's what research is really all about. You have to figure out what elements do you need in the model to explain the data. And if it turns out you need a messy model, you need a messy model. But if it is, you can strip down the model to its really core and say, look, I'm going to go to the core 3 equation Duquesne model. I'm just going to add 1 dimension to it. You can get away. You can get this far. Okay? But is this the end of the discussion? No, absolutely not. And I think that's what drives you, and that's what drove the authors to consider extensions of their model. So now, if you read the paper, right, they have done a lot of extensions to their model. that make the model more complicated and not nearly as transparent and easy to understand. And what do they find? And so that's basically the way to do a macro these days. You're trying to build the smallest possible model to make a point, and then you're looking, if you extend the model, make the model more realistic, more complicated, what are the things that you're going to get then? Are the results going to be on top of each other? It's like, is everything upside down, so the small model is not useful at all? Or do the results, are they robust, or they're always going to go in one direction? That's the key. And that's what they do here.
Okay.
So the first thing they do is, obviously, they put in capital production function. And then what they show is the inflation effects get larger. And so by including capital in the production function, you're going to get inflation from greenflation and climateflation goes up by more. That's the first key effect. What's that? Why is that? Well, if you read the paper, you're going to learn because there is this abatement spending and this rise in the real rate that both drives consumption down. It's also going to drive down investment in physical capital down the road. The real rate increase by the central bank, right? That real rate increase, right? When the central bank raises the real rate in response to inflationary pressures, then when real rates are high, investment is typically low. There's less of an incentive to invest as much. And when investment is low, there's less capital there. And when there's less capital, inflation is going to go up by more because there's you're missing one buffer basically. That's one other thing. Okay? Another thing is that you have this abatement spending surging, and when you have abatement spending surging, it crowds out private investment. So in both cases, capital is going to fall, and the marginal product of labor is going to deteriorate. Okay? So it's going to become more expensive for firms to produce. In other words, you have marginal cost going up. It's now because capital is scarcer, and if capital is scarcer because of investment declining, the price of capital is going to go up, and marginal costs are going to go up, and you're going to have more inflation. So that is, if you put in capital, you're going to get very similar results, except that inflation is going to go up more. All right. Then what they do is they look at redistribution. We have these poor and rich households, and we haven't talked really a lot about the redistribution. How are they kind of compensated, the rich versus the poor? So you can put in fancy schmancy redistribution schemes, like redistribution in a progressive way. That the richer you are, you have to pay higher taxes than if you're poor, also at the margin. And what they show is that that leads to more inflation. You're going to have even more inflation than what we looked at. So I guess it's not a surprise if I just highlight that, right? The answer is always yes. So meaning, if you put in all these features, inflation is going to go up more than in the four equation version of the model. That's the idea. So you're putting in sticky wages. So another thing is that here wages can adjust quite a bit. Wages are quite flexible in this model, and the way to see this is if you go to the dissecting the Phillips curve, you see the wages are dropping a lot. Now, we know that many time series in macro are sluggish, and importantly, if you look at micro evidence for wages, they are quite sticky. So wages move only relatively gradually. So the model misses stickiness in wages. So wages that have a similar Rothenberg adjustment cost for wages. We have one for prices, and think about there's unions that decide up on a wage, and those unions, when they want to change the wage, there's like a Rothenberg cost of the wage. That's what they do here. And then what you're going to see is you're going to get more inflation. Why is that? Well, because notice the wage inflation effect is deflationary, right? So that brings inflation down, right? And if wages cannot fall as much, so if wages are, because of wage stickiness, bound to not fall as much, it's going to push up inflation. So with sticky wages, you're going to lose this downward force on inflation. That downward, so those numbers will be higher than this. Instead of wage inflation going by -5, wage inflation may go by -2. And that's of course going to push up inflation as a result. And then finally, they also look at what's called the optimal transition. So that is the SSC, that's the social cost of carbon, the social cost of carbon. So the idea is they're looking into the welfare maximizing transition. What is the welfare maximizing transition? So how can I explain that? In this model, right, we have this path for the carbon tax is chosen not on a welfare perspective, but this path is chosen to bring emissions down to zero. That's how the green path is calculated, to bring down emissions to zero. Who says that's welfare maximizing? Who says that's maximizing the welfare of the households? So that's why they do yet another analysis and asking, how does this path need to look like so that welfare is maximized in this economy? Households are best off in a sense, right? The household utility is maximized. So what path of Tau do I have to choose so as to maximize welfare? And it turns out you're choosing a non-zero path. So that also has costs and benefits, but the one thing that is really important, the resulting dynamics are such that you want to get faster to zero. You want to get to zero not by 2050, but you want to get there by 2030 or so. So you have to ramp up the tax faster. Okay? And that means you're going to have more abatement faster. And if some stuff happens faster, means there's more, that's going to push up inflation because there is now even more demand, in the short run to a larger extent. And so they showed that the optimal transition also involves inflation going up more than what we have. So in fact, what you can do is you can view the results that I've shown you on inflation as a lower bound. We have established essentially that those inflation effects that we see on total inflation is like a lower bound. If you increase capital, it will go up. If you increase redistribution, it will go up. If you make sticky wages, it goes up. If you do optimal transition, it goes up. So these results here, you can think about, extensions of the model that are more complicated will make this, inflation go up by more than what the baseline model suggests. Okay. Are there any questions on this? Well, if not, then let's move to the last subsection or last element of this paper, which is a very important element. So let's now think harder about, through the lens of this analysis, what are the implications for monetary policy papers? I mean, we started this about, not a week ago, but on Wednesday we started with this, right? With the first slide, going back to Isabel Schnabel and portraying that central bankers are worried about climate inflation and about greenflation. And we have now crafted the model, and we understand what the quantitative results are. We are now able to quantify that climate inflation and greenflation are substantial objects. So we're not talking, it's a fraction of a percent point or so. Inflation goes up because of climate change. According to the analysis, inflation goes up by 2-3% for persistent periods of time because of climate change. So that's a substantial increase in inflation that central bankers are worried about. And now is the billion-dollar question, okay, is there something that the central bankers can do about this? Because all the results that we studied so far, folks, right, they are conditional on the central bank using this tailored rule, right? All the results that we have studied so far is based on this Taylor rule, which explains past data quite well, but the question is there another configuration for monetary policy such that inflation may not go up as much? Okay. That's what we're trying to understand now. So the implications for monetary policy part now is exactly zeroing in on that. What can the central bank do? Or should the central bank do? we do this now in practice? Well, it basically is going to boil down to how we are designing so-called monetary policy rules. And one rule is what we have already worked with, is the so-called Taylor rule, right? So the Taylor rule is one such rule. And what does this Taylor rule say? Well, we want to stabilize inflation relative to an inflation target. Phi is a coefficient, right? And if inflation is higher, say, than the inflation target, you're going to raise your policy rate relative to the steady state. That's what implicitly is the Taylor rule, right? So that's the Taylor rule we've been working with in this course so far. Now, what's important there is that this R is the so-called steady state. It's the steady state interest rate. So think about this as like 3% or 4%. All right. So that's what one way to think about that. Now, what they are examining here is the question: should the central bank move the interest rate relative to the steady state interest rate, or should they possibly move this relative to the so-called natural interest rate? We have to explain what the natural rate is, but that's going to be the bulk of the analysis in this section of this paper. So let me first show you what they are doing, and then we're going to try to explain what the differences are. So this is the equation that they have estimated in their model for central bank monetary policy, right? So we're stabilizing the interest rate relative to the steady state. They are then comparing that to what happens if they are stabilizing it relative to what they call R star. That's the only difference of what they're doing. And what is R star? Well, R star is it's the product of the real equilibrium rate and the inflation rate. So that's what this is. Now these are gross interest rates. So this is the gross rate, the gross real rate, right? And this is the gross inflation rate. So everything is in gross terms here, right? So that's why this is multiplied. So that's the so-called R star adjusted rule. So who of you guys have heard about R star before in your lives? Have you heard about what R star is? Have you heard about that? Okay, so then we need to back up a little bit on this one. What is R star? R star is the holy grail for central bankers. If you know R star as a central banker, you're sleeping very well. You're not losing sleep at night worrying about it. Central bankers worry a lot about R star because they are trying to set an interest rate. Okay. R, that's the normal policy rate. That's like 5%, or you go to that's the normal interest rate. R star is the so-called natural interest rate, or it's the equilibrium interest rate, or it's the interest rate with flexible prices. So this is the interest rate that would occur when all prices are flexible. We learned on Tuesday and Monday that the natural level of output is the output that is efficient in this economy. You take away price stickiness, that's the efficient response of the economy. Likewise, you can think about R star is the efficient level of the normal interest rate in this economy. Problem is it's not observable. You cannot observe this. You have to estimate it. But let me maybe put a little more detail on what this R star is, given that you don't seem to have had it covered in your courses. Okay, so let me write down what R star is. So let's write down, if you have a model with flexible prices, so how does a flexible price economy look like? You have an Euler equation in that flexible price economy. So you have an Euler equation that looks like this. So I'm going to drop the expectations operator, so there's no expectations operators. But one way to think about the flexible price economy looking like is something like this. operators. So again, forgetting about expectations operators. Where this is the, the level of consumption with flexible prices. This is the level of the nominal interest rate with flexible prices. This is the inflation rate with flexible prices. And you can show that this is the efficient response of the economy to any shock. So if there's a shock happening in this economy, right, it's the best way to send the interest rate could adjust, or the efficient way, right? So in slide number 2, you know how we named this in slide number 2? In slide 2, we named this YTF. That's how we named this. Was the notation in the slide deck number 2. It's the flexible price or natural level of output. Okay? And if you have a natural level of output, then of course you're going to also have a natural level of interest rate, and that's what R star is. So if you, as a central banker, have a little bird chirping in your ear, oh, R star this period is 4%. That solves a lot of problems, because then you could try to set the actual interest rate such that you're going to attain the optimal 4%, right? If somebody says, if God tells you the interest rate that in the efficient economy is 4%, so that's the efficient level of interest rate, and your interest rate is 3%, well, that interest rate is too low relative to the efficient economy. That's the basic idea. So, in terms of understanding where this goes. And then, of course, the ratio, right? The ratio of R star to pi star is what the literature calls the real R star, R star, right? And also what the people calls that. All right. So that's the flexible price economy. Now let's write down the sticky price economy, and let's see where does R star show up there. And that's what we're going to do next. We're going to write down the sticky price economy. That's the sticky price economy. Okay. And there we have the so-called IS equation, right? We have the investment and savings equation. And that says something like this. Again, I'm leaving out the expectations operator, right? It looks like this. Minus, open parenthesis, RT minus pi t plus 1. This is now, of course, all in deviations. And then minus RRT star. And there we go. So that's what in the flexible or in the sticky price economy you typically get as the IS curve, right? So again, in slides number 2, right? How did this look like in slides number 2? So if you look at slides number 2, then RRT star head was nothing else than just alpha ZT. Right? So if you go to slide number 2, let me take a look here. If you go to slide number 2 to the equilibrium set of equations, that's this one. Forget about this, right? There is alpha ZT here. You can move the alpha ZT in here, right? And then you have minus the nominal interest rate minus expected inflation minus alpha times ZT. In here. That's all I'm writing down. Okay? That's what we have here. So in other words, R star is alpha times ZT through the lens of this little kind of node here. So in other words, when technology shocks hit, it's moving R star around. It's moving the efficient real interest rate, the flexible price real interest rate. We shouldn't be surprised. That's the standard RBC effect. But now comes the kicker. Notice that now, where do we see the holy grail? Why is R star so important? The real rate important? Well, you see, if the central bank manages to set the equilibrium real interest rate in the economy equal to R star, what's going to happen to the output gap? The output gap is always going to be 0. That's the holy grail. If somebody tells you R star is 4%, and you figure out the magic sauce to set the real interest rate in the economy to 4%, you're going to cross the output gap in all points in time. So let's write this down. So if RT head minus pi t plus 1 head is equal to RRT head star, well, that means that the output gap is equal to 0 for all periods in time. So output is always at potential. So output YT hat is always equal to output in the fixed price economy. That's the key. So that's why when the central bank knows our star, it can design a normal interest rate policy such that the real interest rate in this economy looks like the real interest rate in the efficient economy. And then it can achieve a welfare maximizing level of economic activity such that output here in the actual economy equals output in the flex price economy. This is a hypothetical economy but welfare maximizing, but we can design interest rate policies like that. So knowing our star is important because now we can think about what is our star. Well, that is equal to RT star, the normal interest rate, minus pi t plus 1 star. So that's why the central bank would love to know what the real rate is, because then, given some inflation target, it could pin down what the normal rate it would like to target is. That's it. So that's, if you ever wonder about why are these central bankers obsessed with our star, it's exactly because of that. It allows the central bank to achieve, so to say, an important benchmark in terms of economic activity. Now then let's go back here, right? So that's basically the background to all this analysis now. So they're now asking, okay, suppose the central bank stabilizes the interest relative to some steady state interest rate, or as an alternative, what happens if they're trying to stabilize this relative to our star? How does this have any effect on the transition for this climate economy? Does this have any effect on inflation and so forth? Now, to say this first is that in standard DSTE models, this is roughly equal to this. For instance, if you don't have technology shocks, then this is actually equality, right? If you don't have technology shocks or anything that moves around this, then this is equal. These two things are the same. Okay, so in standard models, the steady state interest rate and our star are often very similar. Like if you only have cost push shocks, right? Then this thing doesn't move, and this is the same as this one. So in standard models, kind of not so important. I mean, I should be careful saying this, but it's not so important then, for instance, it is here, because as we will see, with the climate model, now we're going to see big changes in our star, and we're going to see big changes in Y star. And then we're going to learn that that's going to have a material effect on how the central bank can stabilize the economy. All right. So let's do an example, or let's put this let's put this in. Okay. So first of all, let's look at potential output here. Okay, so this is natural output. In slides number 2, we call this again YTF. And what you see is potential output. So this is how output evolves in this economy with flexible prices. If you have the laissez-faire, then output is just going to decline because of the climate damage. When you have the Paris, it's initially going to decline by more, right? Because of the carbon tax and the mitigation expenditures and the central bank. But then going forward, output is going to exceed the laissez-faire because you're going to have fewer climate damages, so the economy can operate on a higher trajectory in terms of output. Now, as a result, you can of course also compute R star. So this is now the natural real rate, R star, okay, which is the product of the nominal rate times inflation. And then you see that R star is very different in the two economies. Right? So this is R star in the laissez-faire economy. Okay? And the green is R star in the climate economy. The difference are coming from the carbon taxes affecting potential output. The mitigation affects potential output. And you can see that they're very different. Now, what is this yellowish line? This yellowish line is the steady state normal interest rate. So this is the steady state rate. Now you got to be a little careful. So SS means steady state. This is steady state. This is steady state. So you see that the laissez-faire is relatively close to the steady state. Okay,
So if you were to stabilize the normal interest rate or, relative to its steady state, this wouldn't be much of a difference. But it is very different from the R star under Paris. So through the lens, and this is where really the idea is coming from, that now when you are stabilizing relative to steady state, so suppose you're living in this green world, and this is R star, but you will be stabilizing the economy somewhere down here. So the interest rate is too low. The interest rate is too low relative to the efficient level of the interest rate. So monetary policy is too expansionary. That's the basic idea. If you are stabilizing, the R star or the interest rate around this level of the interest rate, then you're going to be too expansionary. You're going to boost inflation. That's the problem with this rule. And so that's what this is. That the natural rate is persistently higher, right? It's a measure of resource scarcity, and because you have lots of mitigation spending, there's like more scarce output, and so that's why if you want to borrow, you have to pay a higher rate because of that. It's a booming economy at that point. So that's why R star is higher. And if this is the efficient level of the interest rate, but the central bank, stabilizes the interest rate somewhere here, then you're going to have a big difference. The interest rate is too low relative to where it should be in the efficient allocation. That's the key. And so monetary policy, there's a chance that policy is too loose, is too expansionary, keeps the interest rate for too low. And we know in the New Keynesian model, when you cut the interest rate, what's going to happen to inflation? What's going to happen to inflation when you cut the interest rate? Exactly, inflation goes up. So the inflation dynamics that we are studying could be elevated because of the too loose monetary policy stance. Because the central bank, right? So suppose this is 2%. So the central bank stabilizes the interest rate around 2%. But suppose this is 4%. And the central bank will stabilize the interest rate relative to 4%. Now this is a much more restrictive stance than this one. So that's the whole idea. At the level by which this thing is moving matters for the allocations. So that's the idea. So let's see, just as an example, like for instance, 2% here, and suppose, just as an example, 4% here, right? Then of course, RT here will be much higher than there, and thereby slow down inflation as a consequence of this. And that's what we see. That's exactly what we see in this analysis. Now, right, so we have, these are now the inflation trajectories. Notice this is now an annual percent, so this is the only graph in this whole slide deck where they have annualized for us, so we don't need to multiply by 4. Okay. The green is the baseline, so that's the baseline. But you see that over a window between 2030 and 2050, as we discussed yesterday, inflation hovers around 3%. That's what we discussed yesterday. And now they go with the, this is the rule number 1. Okay, so on the previous slide, this is rule number 1, and this is rule number 2. So that's rule number 1. And then they switch out the rule and put this rule in, and they have this this orangey line that gives you the allocations with this rule number 2. And you see, indeed, the central bank is going to be able to deliver a much lower level of inflation with the R star rule than with the R rule. That's the idea. So inflation is really coming down, quite substantially as a result for that. Now, so in other words, this illustrates that that this rule delivers better inflation outcomes. Let me ask you: is this a free lunch? Is this a free lunch in the sense that we have lower inflation and everybody's happy? Somebody said something. Was it? Exactly. Right. So output as a consequence is lower because If the central bank, maintains a higher level of interest rate, it's going to cool demand. And that cooling of demand is going to lead to lower inflation, but demand cooling means you have less demand in the economy. And that's what you see there. You're going to have less output, okay? So output is going to fall as a consequence as well. So inflation does fall. That's good, but it comes also with less income. Now, are the differences here large or big? I don't know. I'll leave it up to your judgment, whether you're thinking that this is a big change or a small change on output. Okay? You get a couple of percentage points on output. You get like quite a substantial kick on inflation, but that in the end, maybe warrants also a wealth analysis on what you think are the effects coming from this economy on output. Are there any questions? So what did we learn from this? We learned from this that a seemingly small change in the policy rule for a central bank can have a relatively substantial effect on inflation outcomes and also affect output outcomes. Be always mindful. And this only happens if the steady state interest rate is substantially different from the flexible price interest rate path. Only then that's going to happen. Of course, if this is equal to that, then we're going to see virtually no change. Beautiful.
Sorry.
Yeah,
Can I ask a quick question?
Yeah.
In our model, is there a way for us to kind of like specify what stage of the economy that we're looking at, like whether this is a developed economy or like emerging economy?
Oh.
Because say like if we're looking at a trade-off, like if for a developed economy, a couple of percentage point output is a lot, but maybe if you're looking at a country like Vietnam or China, it doesn't matter much.
That's right. Good point. No, I mean that's a fair point, right? So this is all this is all done on the world economy. Okay? So the way this model has been, specified, estimated, taken to the data. This is world data. So you have to interpret these parameter estimates and the model specification as representing the average world economy. We can think about, wait a second, the average world economy is maybe, that's not the US and that's not Thailand or Togo in Africa. Right? So one alternative would be to maybe re-specify this model for a particular country. Take this model and say, take it to Vietnam. And then through the lens of the model, you need to have re-parameterized the model parameters and then understand how much does this affect Vietnamese inflation or output in Vietnam. And is the percent change, that results, say, on output from that analysis is big or small, relative to if you were to take this model to US data. That's basically, that's the beauty of this, that you can take this model to different countries. Now, we have to be a little careful. When you take this to different countries, you have to make heroic assumptions, right? A little bit, in the following sense, because from a world perspective, if you look at that carbon constraint, or if you look at that climate change equation, right, that's the worldwide carbon stock. So the first three equations, you can always think about country equations, right? Phillips curve, the IS curve, the monetary policy, you can always tailor that to a particular country. But the climate change, this is of course the atmospheric level of carbon in the entire world. So that's not so simple to do, right? So here is world output that affects carbon at the global, sphere, basically. Now, if you want to take this model to Vietnam, say, you don't want to think about that Vietnamese GDP is the only contributor to the carbon level in our globe. So that's what people then do is, they are saying, they're writing down these equations and then they're writing like emissions from the rest of the world. So they have ET from the rest of the world. So you can think about, you're splitting the emissions going into the carbon stock from Vietnam and the rest of the world, so outside Vietnam. That is then could be driven by another set of three little equations, right? So you could think about you have three equations for the rest of the world, a Phillips curve, an IS curve, and a monetary policy, and then this will start to become a two-country model, like one for the rest of the world versus Vietnam. Or you could keep this also exogenous. You could say there's an exogenous stream. Think about this is China, right? So China produces a lot of emissions. That's what China is. And then you're going to study what's the impact of Vietnam. And then, the impact of Vietnam will be very small because it's a small economy, but it's non, so to say, negligible either. But you will still be able to use the model and to understand what does climate inflation do to Vietnam. Because it will give you, if the rest of the world does more emissions, and you can think of if the US or if China keep on emitting like crazy, it's going to blow up the carbon in the atmosphere, and that's going to give you all the climate damages that you see. A tax in Vietnam will reduce emissions, but it will have most likely a very small effect on the world carbon stock. But you can still, try to understand what does a carbon shock do to, the Vietnamese economy in terms of a carbon tax shock and so forth. So if I were you and you're saying, you may be interested in applying this to Vietnam, that would be a specification that I would start developing further. And then you can answer questions like, take this model to the US versus Vietnam, what are the differences? That's a beautiful paper. That could be a thesis, that could be a paper, stuff like that. So that's the beauty of the sandbox that I was, that I'm bringing here for you guys, because I think there's a lot of great economics and a lot of technicalities that could be applied. All right. Any more questions? Now, there's one more beautiful analysis. That's like another 3 slides, and then that's the end of the talk, or the end of the slides. But I will not be able to do this in 4 minutes, so why don't we do the following? Why don't we take a break now? And after the break, I need 10 minutes, and then we'll finish the climate. Okay. So let's reconvene. Let's restart the lecture at 11 sharp. So be here a minute or 2 before 11 o'clock. Okay. So we're going to restart the lecture at 11 o'clock sharp. So be here like 1 minute before 11 o'clock, please. Okay. And then we're going to be perfect. Excellent.